Hello, this is Rick from MathX, and today we'll be doing the number 24 from the AMC 8 of 2018. Now, what I thought was really interesting about this AMC 8 problem is it incorporates 3D geometry, and this concept is typically reserved for AMC 10 and beyond kind of exams. Because of MAA's choice to include this concept on the AMC 8 test, I think that this problem is actually quite interesting. And in my opinion, this problem was probably the best problem on the 2018 test. So without further ado, let's just get into it so I can show you how great this problem is and how simple the solution is. In the cube ABCDEFGH with opposite vertices C and E, J and I are the midpoints of edges FB and HD respectively. Let R be the ratio of the area of cross-section EGCI to the area of one of the faces of the cube. What is R squared? So the problem is quite simple. We have a cube and we have this weird shape that is formed by taking the cross section of some corners and some midpoints of certain edges of the cube. It wants us to know what is the ratio of the area of EGCI to any normal face of the cube and wants us to square that value we obtain. So obviously, the first step would be to compute for this ratio, the ratio of EGCI. And then once we compute for the ratio of EGCI to one of the faces of the cube, we would just square that value and obtain our answer. So since we're asked to find a ratio here of EGCI to the area of one of the faces of the cube, to make the problem much simpler, we can just think of the area of one of the faces of the cube as 1. If we just take that the area of one of the cube's faces as 1 and label all the lengths and areas as such, we just need to find out what the area of EGCI would be when the area of one of the faces of the cube is 1. And then we can just take that value, because when we take the ratio with respect to 1, we're just going to get that ratio itself. So by taking the area of each cube face as 1, we've just simplified this problem into solving for the area of EGCI in a unit cube. So that makes the problem much simpler. Using that, we can see something interesting with all the sides. Side EJ is the hypotenuse of a triangle with sides FJ and FE. Since we're treating it as a unit case because of our original condition, we know that FE is 1. And then since in the problem it says that J is the midpoint of FB, which is also 1, FJ is 1/2. Thus, the length of JE, the first side of quadrilateral EGCI, is just the result when using the Pythagorean theorem on 1 and 1/2. Similarly, if we look at the side JC, it is also the result of using the Pythagorean theorem of 1 and 1/2. As we can see, JB is once again has a side length of 1/2 as its half of FB, which has a side length of 1, and BC has a side length of 1 because it's an edge of a unit cube. This pattern follows for all the sides of EGCI, and it's clear that because they're all a result of the Pythagorean theorem when used on 1 and 1/2, all the sides of quadrilateral EGCI are equal to one another. Since all the sides are equal to one another, it is clear that EGCI is a rhombus. So we know that quadrilateral EJCI is a rhombus, because that's the definition. A rhombus is a quadrilateral with all its sides having an equal length. So now that we know that EJCI is a rhombus, let's think. How would you compute for the area of a rhombus? It's quite simple. To compute for the area of the rhombus, we just use the formula A is equal to D1 D2 by 2, where D1 and D2 represent the two diagonals of the rhombus. So if we want to just find the area of EJCI, which will help us get the ratio of EJCI to the area of one of the faces of the cube, which we can square for the answer, we just need to compute for two diagonals of EJCI, a D1 and a D2. So let's start. Let's take D1 as the diagonal from E to C. Well, the diagonal from E to C is actually quite simple to compute for, because E and C are opposite vertexes of a unit cube. To compute for the length, we just have to use Pythagorean theorem twice. Using Pythagorean theorem to get the length from E to D, well, since each side has this length of 1, we would just do the square root of 1 squared plus 1 squared for the length of E to D, giving us root 2 from the length of E to D. But since we're trying to find the length from E to C, we take this root 2 and we apply this Pythagorean theorem with this root 2 and this 1 from side length CD to find out the side length from EC. Because taking ED and CD, we have another right triangle that we can use to find the length of EC. So using the Pythagorean theorem once again, we see that EC is root 3, because if we apply the Pythagorean theorem to ED and CD, well, ED squared would just give us 2, because ED itself is root 2, and CD squared would give us 1, because CD is 1. So it is clear that root 3 is the length of EC. So thus, D1 is root 3. Next, we have to compute for the length of the other diagonal, which we can take as JI. Now, JI looks a little bit tricky, but there's actually something really interesting about it. The length between JI is the same as the length between BD, or any diagonal between the square sides of the cube. And that's because JI is just the result when BD are both moved up by a length of 1/2. So thus, in order to find out the length of JI, diagonal JI, which we can use to find the total answer, we just need to find the length between BD. And this, we can just use simple Pythagorean theorem. Just as we computed for the diagonal ED, we plug in 1, and we plug in 1 once again, and then taking the square root of the sum of their squares, square root of 1 squared plus 1 squared, we get that root 2 is the length of B to D. Thus, root 2 is also the length of JI. Thus, the length of D2 is root 2. So then, substituting this into the equation, we get that A is equal to root 3 times root 2 over 2. So this gives us the area of cross-section EJCI. And we don't even need to take account for the area of one of the faces of the cubes, because remember, we set that as 1 in the very beginning of this problem. So if we want the ratio, we would get R is this value divided by 1. However, that won't make a difference to this value at all. So we get that R is root 3 times root 2 by 2. Now simplifying for R, by multiplying root 3 by root 2, we get that R is equal to root 6 by 2. Now here's the thing. In the problem, it asks us for the value of R squared, not R. So even though we got that r is root 6 by 2, we still have to square both sides. Squaring both sides, we get that r squared is equal to 6 by 4. And anybody who knows how to reduce fractions will automatically notice that 6 by 4 is just 3 by 2, which is our answer C. So we see that this problem isn't too hard. We just had to identify that EJCI was a rhombus. Use Pythagorean theorem a bunch to get the diagonals we wanted. And then using our neat and clever little trick, we just eliminated the area of one of the faces of the cubes by setting it to 1. So then, by computing for EJCI, we get the answer itself, and we just need to square that to get a circleable answer.